Assalamu alaikum. Today is lecture 11A. So lecture 11 is divided into two parts. So this is first part of lecture 11. In last lecture we discussed about the Euler's criterion, according to which if P is an odd prime and P does not divide an integer A, then A is quadratic residue of P if and only if A to the power. So A is quadratic residue of P if and only if and only if A to the power P minus 1 by 2 is congruent to 1 modulo P. Okay. And the condition is P is an odd prime P is an odd prime and P does not divide A. Then A is quadratic residue of P if and only if A to the power P minus 1 by 2 is congruent to 1 modulo P. Okay. In last lecture, we discussed about the proof of this result. So by using this result, you can easily find whether the integer is a quadratic residue or not. For example, look at 11. Okay. So whether 11 is a quadratic residue of P if P equals 13. Okay. Then 11 to the power 13 minus 1 divided by 2. Okay. So this is same as 11 can be written as minus 2 and 13 minus 1, 12, 12 by 2 is 6. Okay. So 2 to the power minus 2 to the power 6 is 64 and 64 is minus 1. So minus 1 is not, because 11 to the power 13 minus 1 by 2, which is minus 1. So 11 is not a quadratic residue of 13. Okay. And then look at 10. So 10 to the power 13 minus 1 divided by 2. So this is again 6. So minus 3 to the power 6. And this is congruent to minus 3 to the power 6. Okay. So you can write minus 3 square times minus 3 square times minus 3 square. So this is same as minus 3 square is 9 and minus 3 square is again 9. So 9 times 9 times 9, and this is 9 times 9 is 81, and 81 is 3 in modulo 13. So 3 times 9 is 27. 27 is 1 modulo modulo 13. So 10 is a quadratic residue. Okay, so this procedure is a little bit easier than the previous one. Okay, so this is modulo 13. Okay, in this case we don't need to solve quadratic congruence. Okay, so once we have information about the whether the integer is quadratic residue or not, then we can easily decide about the quadratic congruence, whether it is solvable or not. Okay, so so if a to the power p minus 1 by 2 is congruent to 1 modulo p, then a is quadratic residue, and with all the conditions, okay, if to the power p minus 1 over 2 is congruent to minus 1 modulo p, then so this condition is with if and only if condition. Okay, so better to use to write if and only if a is a quadratic non-residue. Okay. Okay, now move to the another thing, and this is a little bit stronger than the Euler criterion, and let me introduce a new thing in this lecture, and that thing is Legendre symbol. Okay, so the Legendre symbol. Okay, so if let P be an odd prime, and the previous one is also for odd prime. Yeah, I have written odd prime. So let P be an odd prime, and a any such integer such that P does not divide A, then the Legendre symbol is represented by A, Legendre symbol of A by P, okay, in parentheses. So it doesn't mean that P is dividing A or it's a quotient of A and P, okay, but if we write any integer oblique prime, okay, P is any odd prime in the parentheses, so it means it's a Legendre symbol. Okay, so the value of the Legendre symbol is 1 if A is a quadratic residue. If A is a quadratic residue, and minus 1 otherwise means quadratic non-residue. Okay, so that's the definition of Legendre symbol. Okay, this is very important. So, for example, we know that 1 is a quadratic residue of 13. So, and 4 is also a quadratic residue of 13. 9 is also a quadratic residue of 13. 10 is also a quadratic residue of 13. And 12 is also a quadratic residue of 13. Okay. So all of them are quadratic residue. So the value of Legendre symbol for all those is 1. Okay. And 2 is not a Legendre symbol. 2 is not a quadratic residue of 13. And 6 is not a, or let me write 5 as well. So 5, 13, 5, 6 is not a not a quadratic residue. Is a quadratic non-residue, and 8 is a quadratic non-residue. 11 is also quadratic non-residue. So the Legendre symbol of those values is -1. And we have 3 as well. So 3 is a Legendre symbol. So then 3 by 13 is 1 or so, and so on. Okay. So now we can rephrase Euler's criterion, because according to Euler criterion, if A is a quadratic residue, so if you look at the Euler criterion, so if A is a quadratic residue of P, if and only if A to the power P minus 1 by 2 congruent to 1 modulo P. So we can rephrase Euler criterion. So according to Legendre symbol, so Euler criterion will become A is a quadratic residue of P if and only if Legendre symbol of A is 1. Okay, so that's simple. Okay, so this is Euler criterion. Euler criterion by using Legendre symbol. So let P be an odd prime, then a positive integer, then a positive integer A, with the condition that P does not divide A, is a quadratic residue if and only if Legendre symbol of A for P is 1. Okay, so we can find Legendre symbols for any integer. Okay, then we'll be able to comment about, or we'll be able to find whether the quadratic congruence is solvable or not. Okay, so okay, let's do a theorem. You can call a theorem number. Okay, what should be the number? Let me check. Number 4, Theorem 4. Okay, so this is Theorem 4. Let P be an odd prime. Let P be an odd prime and A and B be any integer A and B be any integers with P does not divide the product AB, then one, if A is congruent to B modulo P, then A, Legendre symbol of A is equal to Legendre symbol of B. Number 2, Legendre symbol of A for P times Legendre symbol of B is equal to Legendre symbol of AB by P. 3, Legendre symbol of A square is always 1. Okay, so look at the proof of all parts. So proof for 1. Okay, so it is given here P is an odd prime and A and B are any integers with the condition that P does not divide the product AB. Okay, so P is not dividing the product A and B. Okay, and we suppose the condition A is congruent to B modulo P. Okay, so if A is congruent to B modulo P, then the congruence x square congruent to A modulo P is solvable if and only if and only if, okay, if and only if x square is congruent to b modulo p is solvable, is solvable. Okay, so x square congruent to b modulo p is solvable. Okay, so because we have assumed that a and b are congruent modulo p, so then the congruence is only solvable if and only if the other congruence is solvable. So if both of the congruents are solvable, okay, or not solvable, okay, then in both the cases, in both of the cases, Legendre symbol of A is equal to Legendre symbol of B. Okay, so that's first part of the result. Now move to the second part. Okay, in second part, by Euler's criterion, okay, so it is given here the product of two Legendre symbol is the product of A and B. So A, B, so I'm using here Euler's criterion. So according to Euler criterion, Legendre symbol of AB is equal to AB to the power P minus 1 by 2 modulo P is congruent to mod, and this is congruent to A to the power P minus 1 by 2 times B to the power P minus 1 by 2, okay, and this is congruent to A, P and Legendre symbol of B. Okay, so that's the modulo P. So P is an odd prime. The value of Legendre symbol is 1 or minus 1. Okay. So in both of the cases, if okay, so this inequality hold in both of the cases. Number 3. Okay. So AB. So it means A times A, Legendre symbol of A times A. So we are using 2. So this is same as Legendre symbol of P, Legendre symbol of A times Legendre symbol of A. Okay. So if and this is equal to, because if Legendre symbol of A is 1. So if A, let me erase this one. So if Legendre symbol of A is 1, then A square, Legendre symbol of A square is the product of 2. So it means 1 times 1, which is 1. And if Legendre symbol of A is -1, then Legendre symbol of A is -1 times -1, which is 1 again. So in both of the cases, Legendre symbol of A square is 1. Okay. So that's the proof of theorem 4. So inshallah, remaining part of Legendre symbol uh, will we will do remaining part of Legendre symbol in the next lecture, lecture 11b. Okay. Thank you very much. Allah Hafiz.